My name is Javier Camara from the University of York, and I'm going to present HaiQ, Synthesis of Software Design Spaces with Structural and Probabilistic Guarantees. Modern software-intensive systems are commonly affected by uncertainties derived, for instance, from the lack of control over third-party components, for instance residing in the cloud, humans in the loop, and complex interactions between software and physical elements in cyber-physical systems. Designing such systems in a way that provides guarantees that concern the satisfaction of functional requirements while achieving an acceptable balance between multiple non-functional properties is still an open problem because designers typically rely on intuition to navigate these design spaces. This is a difficult problem because system structure and stochastic behavior, as well as their interplay, can distinctly impact functional and non-functional requirement satisfaction when systems are subject to uncertainties. Currently, joint systematic analysis of structural and quantitative or probabilistic guarantees of systems is limited in existing methods. On the one hand, formal methods used to validate software designs like Alloy, Z, B, VDM, and OCL share a common conceptual foundation that enables designers to implicitly describe collections of alternative structural designs, for instance software architectures, database object-relational mappings, or network and security models, a set of relational constraints and exploring them systematically, but they are not equipped for analyzing stochastic behavior. On the other hand, quantitative verification methods like probabilistic model checking can analyze quantitative guarantees of systems, for instance on performance or reliability, under uncertainty, but use notations and analysis mechanisms that do not retain the ability of relational methods to explore structural variability and satisfaction of complex structural constraints. Many application domains of modern software-intensive systems show strong interactions between structural system aspects and quantitative properties that are crucial to deliver their functionality in a reliable manner. Let's look at some examples. In the Internet of Things, network topology and attributes such as distance between devices may have an impact on quantitative aspects such as reliability of communications, performance, or energy efficiency. In microservice-based architectures, service connection topology, interoperability constraints, and service role matching can influence the cost of operating the system, as well as its performance or reliability. In multi-robot applications, robot task matching, robot configuration, and even space topology can impact non-functional objectives concerning timeliness, energy efficiency, or safety. To improve on this situation, our work investigates automated joint analysis of structural and quantitative guarantees under uncertainty. This entails exploring ways of capturing structural variability, stochastic behavior, and their dependencies in models, as well as techniques for analyzing quantitative properties in the presence of structural variability. Our proposal addresses this challenge by incorporating three distinct elements. The first one is a high-level language for modeling structurally variable probabilistic models, which are able to satisfy complex structural constraints. The second one is a temporal logic language called Manifold Probabilistic Computation Tree Logic, or MPCTL, that extends the PCTL temporal logic widely used in probabilistic model checkers. The third element is an extended probabilistic model checking mechanism that enables checking MPCTL properties across collections of structural design alternatives implicitly captured in a HaiQ model. This contrasts with most existing probabilistic model checking analysis mechanisms, which are tailored for analyzing single-point solutions or collections of solutions where variability is limited to parameter values or simple structural changes. We are going to see now an overview of our approach. We start with a HaiQ model, which is a relational and probabilistic behavioral specification of our system. The first step is a structural configuration synthesis, which starts by extracting the part of the code from the HaiQ model that corresponds to the static or structural aspects of the system, encoded in a subset of Alloy. Once the structural description of the system in Alloy is extracted, we employ the Alloy analyzer to synthesize the set of legal structural configurations for our system. The second stage is configuration behavior generation. Here, the first step is extracting the behavioral specification of the different process types defined in a HaiQ model. The second step entails flattening the hierarchy of stochastic process types defined in the HaiQ model, resolving all inheritance dependencies into a set of stochastic process instances. In the third step, stochastic process instances obtained in the previous step are matched with signature instances described in each of the configurations synthesized in the first stage. At the end of this second stage, we obtain a set of stochastic models, each of which corresponds to a legal structural configuration generated in the first stage. Finally, extended probabilistic model checking receives an MPCTL formula that captures a quantitative property that can be checked across the set of stochastic models obtained in the previous stage. As an output, the process can produce quantitative results like probabilities or rewards, sets of configurations that satisfy some quantitative property captured in an MPCTL formula, or Boolean satisfiability results. We are going to illustrate the rest of this talk on a simple network security scenario that models the progression of a virus infecting a network formed by a grid of n by n nodes. In the network, there are low and high nodes divided by barrier nodes that scan the traffic between them. Initially, only one corner low node is infected. From an infected node, the virus repeatedly tries to infect any uninfected neighbors by first attacking the neighbor's firewall. When a node is attacked, there is a probability that the firewall will remain uncompromised and the complementary probability that the firewall will be breached. If the firewall is breached, there is another probability that the node will become infected. The complementary probability will result in the firewall remaining breached, but not infected. In this scenario, structural variability comes from network topology. Here, not all configurations of the network are legal. In particular, all nodes should be reachable from any other node in the network, and low nodes and high nodes should always be separated by a barrier node. We have many legal configurations in our space that satisfy the two constraints we have defined. However, we also have illegal configurations that should be discarded because they violate some of the constraints that we have defined. As we can imagine, variability in the network topology configuration will result in different trade-offs when it comes to resilience of the network against attacks of network viruses. When designing our system, we might be interested in asking questions such as which legal structural configurations minimize the probability of high node infection? Or how many attacks are required to infect all high nodes in the best and worst case scenarios? In order to answer those questions, we are going to start by building a model of our network infection scenario in HaiQ, illustrating the main features of the modeling language. We are going to start by building a model of the structure of the system. This part of the HaiQ model is described in a subset of alloy. We begin by declaring an abstract signature node that includes a relation capturing the fact that a node may be connected to a non-empty set of nodes. We declare another signature barrier node that extends node. And similarly, we include some other signatures that correspond to high nodes and low nodes in the network. We also encode the existence of a single low node that is infected in the network. We can also include some expressions that capture the structural constraints in our network scenario. Concretely, all nodes should be reachable from any other node, a node should not be connected to itself, and connections should be symmetric, and low and high nodes should always be separated by barrier nodes. If we look at this specification, we can see that it captures structural variability in a compact manner, and that this specification is generic and valid for larger problem instances without any changes in the code. However, we can also see that at this point, we are unable to capture quantitative and probabilistic aspects of the behavior of the system. In order to do that, HaiQ extends signatures with stochastic behavior definitions that describe a hierarchy of process types, in which each process type corresponds to a signature. Process variable declarations, formulas, commands, and other elements can be inherited by process types that extend some other type. In the slide, we can see, for instance, how the barrier node overrides the formula detect to include a different probability of attack detection compared to a regular node. Another example is in the infected node, which overrides the initialization of the state variable of the node, setting its value to infected. Similarly to Prism and other languages employed in probabilistic model checking, HaiQ specifies behavior employing guarded commands. Every command is composed by an event which can be explicitly labeled to synchronize with other processes, a guard that enables the command when it is satisfied, and a set of updates, each of which contains a probability and a set of variable value updates. An important feature of HaiQ that contrasts with other probabilistic languages like Prism is that event synchronization is not necessarily fixed in the model. Instead, HaiQ allows an additional degree of freedom in which a synchronization can be left open to any set of related processes bound by a relation. This is specified in the model by prefixing the event with a relation name. In the example, we can see how a node can synchronize on an event attack with any other node that it is connected to. Specifically, we can see that in this case, the node signature process declaration includes two attack events. The first corresponds to the reception of the attack from an infected node, whereas the second corresponds to the case in which the node is infected and attacks a neighbor. These declarations are generic and capture, in fact, any possible combination of neighbor-to-neighbor synchronization, without the need of explicitly defining synchronizations one by one, as it happens in other probabilistic model checking languages. Once we have presented the main features of the HaiQ modeling language, we're going to introduce the temporal logic MPCTL. MPCTL extends PCTL, which is a temporal logic widely used for the analysis of stochastic systems in probabilistic model checkers. PCTL contains state formulas with the classical temporal operators and state formulas that include both the possibility of employing a probabilistic quantifier P able to quantify the probability of satisfaction of a path formula, and also an analogous quantifier for rewards. It is worth noting that PCTL is designed to capture properties of a single probabilistic model. Let's look now into MPCTL. While MPCTL shares the same path formulas with PCTL, state formulas are different, containing existential and universal probability quantifiers. These allow quantification of properties across the collection of probabilistic models within the design space. For instance, these quantifiers allow us to find out whether a solution exists in the design space that satisfies some probability bound of path formula satisfaction, or if all solutions in the design space satisfy some invariant. Moreover, MPCTL contains probability maximization and minimization operators. These enable quantifying the maximum and minimum probability of satisfaction of a path formula within the design space. The logic also includes analogous reward quantifiers. Finally, MPCTL contains a third class of formula called set formula, which enables obtaining sets of solutions that satisfy the temporal logic expression. For instance, we can obtain what is the set of solutions whose probability of satisfying a path formula is greater than some threshold, or what is the set of solutions that maximize the probability of satisfying a path formula. We can see an example of such property here, which obtains the set of configurations that correspond to the minimization of the probability of eventual infection of all high nodes within 50 time units. To capture properties at an usable, adequate level of abstraction, atomic propositions in MPCTL can include existential and universal quantifiers that refer to signatures in the HaiQ model. This enables expressing things such as all high nodes are infected with some degree of generality and without having to explicitly refer to or enumerate the concrete high nodes that exist in a configuration. MPCTL also includes compositional operators that enable capturing sophisticated properties by combining multiple quantifiers, as well as operators that quantify maximum and minimum probabilities of configurations, analogous to Pmax and Pmin in PCTL, instead of the average case shown in this slide. More details are available in the paper. We're going to look now into the evaluation of the approach. Concretely, we looked into 3 different research questions. The first one is about feasibility. Specifically, how can we automate the analysis of quantitative and probabilistic guarantees across sets of structural variants of system designs? The second one is about generality. Is our approach general enough to be applicable to different domains and types of probabilistic formalisms and analysis? The third one investigates the trade-offs of employing our class of approach with respect to existing probabilistic modeling and analysis techniques. To answer these questions, we evaluated our approach in different case studies that include exemplars in the teleassistance and self-protecting systems domains. Details about the application of our approach to these case studies are available in the paper. Here, we will illustrate our results in the context of our network virus infection scenario. In the slide, we can see the results of analyzing MPCTL properties that capture the probability of all high nodes becoming infected over time. On the x-axis, we can see time in seconds, and on the y-axis, probability of satisfaction of the MPCTL formula. The solid lines in the plot depict the maximum and minimum worst-case probability of infection across the design space. That is, the MPCTL properties analyze the worst-case executions across all the existing structural variants of the HaiQ model and return the maximum and the minimum probabilities obtained. This is enabled by MDP-based analysis, in which alternative commands with overlapping guards and without any assigned probabilities in the HaiQ model are interpreted as non-deterministic choices in an MDP. The dashed lines show in contrast the maximum and minimum average probabilities across the design space. These are obtained by a DTMC-based analysis, in which commands with overlapping guards in the HaiQ model are interpreted as probabilistic choices in a DTMC. In the plot, it is important to note that the worst-case analysis provides much more conservative estimates than the average probabilities. Having this kind of analysis available is important for designers who want to provide strict quantitative guarantees about system designs. This kind of analysis is available only by employing exhaustive state exploration techniques across solutions. This emphasizes the usefulness of this analysis technique, because worst-case scenario guarantees in the presence of structural variability would not be available, for instance, employing other classes of techniques like statistical model checking. If instead of the probability of all high nodes becoming infected, we are interested in a more strict resilience property, like one of the high nodes becoming infected, we can change the universal to an existential quantifier in the state formula, obtaining the result in the plot. We can see how the curves shift to higher probabilities, and even though there is a reduced distance between the average and worst-case lines, again, we can see that worst-case analysis still provides a much more conservative estimate for the probability of infection. Basing on our results, we are going to briefly discuss the research questions investigated. Concerning feasibility, we have shown that raising the level of abstraction at which probabilistic models are described and queried can effectively enable joint analysis of structural and quantitative guarantees of design spaces. In terms of modeling, this is achieved by incorporating language constructs that allow structural relations to be referenced from elements of probabilistic behavioral specifications. In terms of analysis, incorporating novel quantifiers to check properties on collections of models in probabilistic temporal logics enables a streamlined specification of sophisticated properties to study guarantees across the solution space. With respect to generality, our results show that our approach is applicable to systems in different domains, in which uncertainty is introduced by disparate sources. Our approach is particularly suited to problems in which structure and topology are relevant and multiple instances of similar but different components that exhibit probabilistic behavior, for instance with different parameters or slight variations in behavior, interact in complex ways. Moreover, we have shown that the approach can be applied to different analyses like average and best or worst case probabilities and rewards, as well as to probabilistic formalisms like MDPs and DTMCs. This is effectively enabled by the fact that HaiQ operates one level higher in the abstraction ladder with respect to existing description languages in probabilistic model checking. With respect to alternative approaches to analyze probabilistic behavior, HaiQ comes with trade-offs in terms of effort, reusability, computational cost, and analytical capabilities. In terms of effort, structure and probabilistic behavior are expressed in a compact manner in HaiQ, and their combined analysis is streamlined. This contrasts with ad hoc solutions that demand developing specific infrastructure and are error-prone. We developed alternative solutions to each one of these case studies we investigated. These required weeks of work, contrasting with single-day specification effort, at most, required to solve the problem with HaiQ in both cases. Other approaches that do not include structural synthesis, for instance direct specification in a model checker, required encoding explicitly all elements of every design alternative, for instance those that correspond to topology, making it more error-prone and orders of magnitude more demanding than HaiQ in terms of specification effort for non-trivial problems. Compared to the ad hoc solutions developed for the case studies presented, which required specific infrastructure, HaiQ provides an infrastructure that can be reused across a range of different domains. Furthermore, the specifications in HaiQ are also more reusable than those of existing probabilistic model checkers, in which behavior types and communication topology are intertwined with the specific instances of processes. In contrast, behavioral type hierarchies can be reused as libraries across the same problem class in HaiQ, since the specifics of instances are encoded separately. Finally, we observed that the computational cost of solving the different scenarios ranged between several seconds and hours. In all cases, however, most computation time was devoted to probabilistic verification, in contrast with configuration synthesis. This kind of analysis is not cheap in computational terms, although there is always a trade-off with the novel analytical capabilities that the approach enables. In this talk, we have presented our work, which investigates the provision of probabilistic quantitative guarantees in the presence of structural variability. Our experience has shown that abstraction is an enabler. In particular, raising the level of abstraction in modeling and temporal logic specification languages allowed joint analysis of structural variability and probabilistic aspects of the design spaces we explored. Preliminary results also indicate benefits in terms of reduced efforts and increased reusability with respect to existing probabilistic model checking approaches. With respect to limitations and future work, our approach is currently limited to analyzing behaviors within specific configuration, but it is not able to reason about behaviors that imply structural changes. Future work will extend our approach to reason about such behaviors. Moreover, we will explore hierarchical specification and compositional verification techniques to improve modularity and scalability.